I think we can start. So just an announcement for you. Today, as I promised you, this week on Tuesday we're going to have a lecture, and next week on Tuesday we're going to have an preparation for the final exams. So if you have any questions regarding the organization or the finals, uh, questions about the content of the finals or questions about the content of the course, just bring them with you next week. And I need to see how far I can get with the lecture today, and if I will still have some time left, so I will continue with the lecture next week. So like I will do the lecture next week if I'm going to have some material left, because that's important. But don't worry, we have 2 hours next week to discuss our final exam, and usually it's more than enough for you to understand what we expect from you during the final exams. So let's proceed. First of all, we're going to speak today about the physical modeling, and we have a short introduction into in-memory databases. And yeah, just let's go on. First of all, you remember that we have different levels of when we are trying to deploy a BI solution. So first of all, we have a conceptual scheme, then we have a logical scheme, then we have a physical scheme. I don't think that you should remember it, but still I have to repeat it. I already spoke a little bit about the physical scheme last time, so while speaking about the tables and performance. And today we are going to a little bit deeper in order to understand what other choices could exist when you deal with the database on the physical level. So basically what I wanted to say you, so nowadays you have multiple types of databases that could be underneath the BI solution. So to name a few, you could have, I'm just exaggerating, it's not usually the case. You can have something like NoSQL database. You can have a relation database. You can have a sort of database that is dedicated to work with multidimensional data. You could have a time series database, or you could have a key value data storage, or you also could have a database that is completely located inside the memory. So all the databases are located inside the memory. I mean inside the RAM. Um, but there are special type of databases that work with that memory as the primary source of truth. So I will just speak on that later. But let's get back to the other aspects. So when we are speaking about the analytical view on the database, you have a sort of two different approaches. There are also third one, hybrid one, but let's stick to two of them. So you have a MOLAP and ROLLUP. So how you could distinguish between them? Um, MOLAP, it's like sort of dedicated database or dedicated type of artifact that deals with the multidimensional data. Basically speaking, you remember during the exercises, we wrote an SQL queries to fetch the data out of the database, and we always were speaking about the dimensions and multi-dimensions. And while fetching the data or while analyzing the data, we were combining the data in some interesting way, like aggregating the data according to one or multiple dimensions. And the point behind the multidimensional cubes, it's that you have sort of all possible combinations in pre-aggregated state. So it means your analytical queries are really, really fast. and this is like transparent to you because you don't need to care anymore about something called materialized views or any other kind of performance boosters. Sorry. Disadvantage is if you have really a lot of data, like let's say a couple of gigabytes or terabytes of the data inside your data warehouse, small up or multidimensional. Online analytics, it's not a good choice. Why? Just imagine when you put a new fact into your table. For this fact, all possible combinations are going to be pre-calculated for you, and so you can get them really fast. So it consumes a lot of space, first of all, and it could be really slow with the time. I wanted to mention to you that it's a good solution, but you have to be aware that it's not always flexible in terms of the data growth. And rollup, it's like relation one. It has a huge advantage. So because it's a database, so you have sort of behind you have a database that is dedicated to cope with any kind of workload. So any kind of workload is a false. It's a false formulation. Sorry. So it's dedicated to deal with generic type of loads. So it's not only dedicated to do with the analytics, it's also dedicated to do with a lot of writes inside into the database. So I mean transactions. And it means basically that if you stick to this solution, usually the one who designs it usually knows what to expect, and the tools that are used there are also quite known and widespread. And you can also stick to the functionality of relation databases. So it's not only the functionality like casting the types or whatever, it's also the tools that could work with this database. You had a bit brighter, you have a bit brighter selection list when you're speaking about the ETL tool, which is quite important. So disadvantage, there are also SQL is advantage and disadvantage. Why? SQL could be a disadvantage because it could change from database to database. So some tricks that you used to use in Oracle won't work in PostgreSQL. So they claim they're all ANSI something, so 92 or ANSI 2001 compatible. But I mean the SQL, but it could be a bit harder to really expect that all SQL is going to be compatible. And SQL on its own is also limited. If you did the exercises again, you thought that SQL queries could be really long. And at once, from time to time, I have to write a script that generates an SQL queries to run them. So because they could be really complex, and it's not feasible sometimes to write them by hand, but still they're really powerful. So here's again the comparison for you. I just already mentioned it to you, so I won't stick to. I won't explain again this table. So let's speak about the database and what database you have to deal with or database requests. First of all, it's good if the database, we're speaking still about the physical level, and so like what you should expect from a database. So support of heterogeneous data sources, so like files, different SQL system vendors, and different databases. So it could be, so your database should be able to deal with those types of things. Then it's also good. Yeah, it sounds a bit strange when we're speaking about the files, but in terms of the database, but here's a trick. So there are a couple of ways how one could require files for a database. First of all, the simplest one is to store a file inside a database. It's sometimes anti-pattern. You can save. It's undesirable if you are saving huge files inside a database, but still, with the modern databases, you can still save up to a couple of megabytes inside a table. So this is like, it's good to know if your database supports that. There's also another aspect is how you could import the files, because usually ETL, it's importing the files. I'm not saying usually always, but sometimes it's the easiest way to deal is to export the file and import the file. Yeah, unfortunately. And so it's quite crucial to see how the database could handle the files. And there is also another aspect that one could be interested in, speaking about the files in the database. You can trick out a database. Just explain you how. Not every database supports this function. So you spoke about the ACID principles. So atomicity, consistency, isolation, and durability. And this is a huge overhead for the database to manage. And just assume that you need to save a couple of terabytes on files inside the database. How you can sort of turn off the ACID principles for those type of data, because you really need to only simplified management of the files. You don't need the fully transactions and so for terabytes of the data that you have. The trick, for instance, in MS SQL, there is something called file streams. So you can sort of say, okay, this is a file stream that I'm going to use for this table, and the database take management of the table, but some particular columns are going to be file streamed to the disk. And so in this fashion, you can overcome this ACID problems, so problems with the transactions and consistency on the data inside the files. Sounds strange, but if you have terabytes of the data and you stick to the database, maybe it's a good idea to deal with the file streams. It's a real project that I'm just describing you. Nowadays, one could maybe use another solution for such type of database, like an object store or whatever, or distributed Mongo cluster or whatever. So then what is also important for the database is to support different types, data types, like time, text, geodata, or multimedia data if it's possible. So it's also possible, why not? An example for you why it's crucial. I think SQLite does not support times does not support or does not work properly with the dates and times. So the workaround is to save the date in the ISO standard and then just get and use it for sorting, for instance, because it's like then a normal. You could then sort a timestamp in the ISO format using treating it as a normal string, but it's still super inefficient. So just to mention you this example, and dealing with the dates, it's my own experience. It's a lot for the database. Then support of the transformation. So what does it mean? It means like integrated into the database part of the ETL tool. So like L or T. So basically it's about a T. So you bring the data to the database and say, now do your magic and transform the data. Yeah, this is also possible. You already saw the schema. So this is basically start schema, and I won't stop on it, but still, again, you have sort of facts inside in the middle table. So it's called fact table, and what's actually a fact. It's on the right side here. So it's like the number that is here, revenue. And on the left side, you have an ID of all the dimensions. Again, without the dimensions, a fact could not have a context, and context has no mean without a fact. So, but you have seen this schema multiple times, and I won't explain it to you again. What I would like to explain you again, or explain you, it's how a typical query on the start schema will look like. So first of all, it's a normal SQL, but a bit so sort of SQL on steroids. Why? Because you have in select, you have sort of dimensions to be displayed and facts to be calculated. Then inside the form, so I don't need to explain you the SQL. So you have select, form, where, group by order. So this is a structured way of dealing with the data inside the database. If you don't know SQL, but if you would like to stay in the data analytics, BI, or whatever, it's a good idea to learn the SQL. It's really a handy tool. Now, let's get back. So inside the select, you have dimensions and aggregations. So this is exactly what we I spoke about when I mentioned to you, hey, you need to pre-calculate, or you need to do something with the data, with your facts. This is exactly what's going on here. In this particular case, it's just a sum. So it's aggregation function. Then you specify the dimensions here. Dimensions include day, product, and for sure facts, because I mentioned to you facts are useless without context and vice versa. Then you specify your filtering criteria with the where, so January, day, and then at the last. So yeah, you're grouping the tables together. You know it as an inner join or a join simply, but I'm doing it usually in this way. So I'm just explicitly mentioning what fields should be joined. In this particular case, you see that order facts day key joined with the day table according by the day key, and order facts product order facts table joined also with the product table, sorry, on the product key and product key. Then you have some sort of group by, so it's the dimensions that you want to look at. So when do you want to combine by, and then sorting. Yeah, I'm explicitly explaining you this again. So for the ones who didn't perform the exercise, so you will get an overview of a typical SQL query for the analytics, what you should usually change. Basically, the structure will stay the same. What you have to change is usually this part, this part, this part, this part, and this part. Sometimes where clause could be a bit more complicated. So or you have to like you could use an integrated queries and so on and so forth. Yeah, as an example, I won't speak on that. And data upload. So we already speak on those topics while we were speaking about ATL. So I won't stop on it. So it's have to be like it have to be fast. You have to have no errors. If something happens during your ETL, you have to know about it. So basically, it's error-prone process. So and if you could manage to control it, it's a huge advantage. QE performance, we also spoke on that, but again, I want to emphasize something that differs open source databases and commercial databases is those query optimizers. So optimizers that are black box for you, but when you run a query, the SQL query, they figure out on their own how the query could potentially execute it within the database in the most efficient way. And there are some tricks that are used. For instance, indexes, and indexes are created to some extent automatically for the primary keys. Why? Because joins are happening on the primary keys. But if you need something more, like then you also could create another indexes. Yeah, and how to do that, and how to deal with those stuff, how to work with those queries, how to explain how to let the database explain you those so-called execution plans. If you're interested in those topics, just check the last lecture that I gave you 2 weeks ago. And there is for sure current state, so what is going on in the database. Basically, it's I would like to stop on the communities are going merging themselves, or let's put it in the let me reformulate. If someone deals lifelong with the machine learning, he or she usually do not use a database, only as the service. So files, pandas, or whatever, PyTorch or whatever, TensorFlow, and that's it. But now in the research, I see the trend that those things, and there is also another community who develops databases. So developing a database or researching in the domain of the database, it's a tough and hard task. And the last community, the database community, existed longer than machine learning community. But obviously now the machine learning community is bigger than the database community. And they're sort of merging on some extent. Basically, it means the databases are getting more out of the machine learning community and vice versa. So it's quite interesting. Then there is, you can see it when you speak. I'll show you an example later on of a memory database that got such functionalities inside the database. So then there is a trend for natural language processing and for sure data visualization. There is also data management problems or data management issues that will exist forever. So for instance, like record linkage or whatever. Then there is also a data management level on the physical level. So there is a distributed databases. Again, we spoke till now about a database as a single instance, but you can also have multiple instances of the same database, so-called cluster, and how to deal with the data management within the cluster. It could be a tough task from the architecture perspective of view. Why? Because when you distribute the data within the cluster, you have to take care that it's equally distributed. And usually some kind of keys within the data is used to distribute the data, and how there is always debates how to select those keys and so on and so forth. So basically you have a keys to say, okay, where this particular row have to be saved on. And there is also data vision, so where we are going to with all those developments. So for instance, so now there are not the discussions actually, but we are streaming. I spoke about the data, about the imports, about the files, and this is usually is known under the term batch processing. So you have an ETL and it runs once in a day or each hour or every minute or whatever. So every minute maybe it's too heavy, but still. So this is called a batch processing. And there's also something called stream processing. It's when you're supposed to have a real-time data or data that will be pushed to your systems at the same, nearly real time. This is hard to achieve, but this tool or this kind of approach um, got a bit different advantages. For instance, um, just imagine you have something like an enterprise service bus. So it's basically where all data are consolidated, and then you distribute the data among the systems. So advantage of such system is that you can create a new system that will benefit from your enterprise service bus. So just um, let's do an imaginary example. You have a ticketing system, and now ticketing system is not enough anymore. Uh, you want to analyze those tickets with some kind of machine learning or whatever, or you want to put them into BI system. If you have an enterprise service bus or something in between, like a stream-based, you only need to build this analytical system and sort of absorb the data from those from those streams. So you don't need to sort of do a huge data integration. Disadvantage: if something happens to your enterprise service bus, you have no data at all. If you have petabytes of the data, then it could be tough to run such infrastructure and so on and so forth. But it's sort of now I see it's implemented in many companies, and the BI as one of the pillars that are benefiting from those stream processing pipelines. And there is also data lakes and in-memory databases. Basically, data lakes is sort of, let's put all our data into some kind of cluster like Hadoop or object storage like Ceph. And when we need the data, then we'll fetch the data. And it's slowly moves to the data swarm because if you have no schema, you have limited ability for data discovery and so on and so forth. And if employee leaves the company and something is not documented, then know-how is get lost or no one knows what the data really mean. So usual problems of the data handling. And here, classical last but not the least, memory databases, that not that trend so far, but they are empowering a lot of applications nowadays. Do you have questions till now? Any kind of questions? I hope it's more or less clear what I'm speaking about. Can you still hear me? Hope you're still awake. Perfect. Okay. Then I would like to speak about something that I called modern data infrastructure architectures. So it's like we spoke about the BI and we spoke about the classical ways of looking at those topics like start schema, relation database management systems, ETL tools. And we also a bit spoke about now I just spoke about the stream processing, but what about current state? How it's like up-to-date view. In up-to-date view, you have something following. So usually you can, first of all, understand, even in a couple of decades later on, I think that we'll still have all those aspects. So like you will definitely have a source data, you'll have definitely an ingestion and transformation, you will definitely have a storage, then you will definitely have something where your queries are running on historical data or real-time data or whatever, and then you will definitely have an output. So all those, they may have different names. For instance, we spoke about the ETLs, and I mentioned a couple of times to you, in modern world, ETLs are called data pipelines. Or ETL engineers could be called data engineers, which is totally fine. Why? Because it's not only rebranding, it's also by calling it data pipelines, you'll also get a bit different view on the data. So it basically means not some guys in BI are just girls in BI are doing their analytics and sending reports to all the employees or to top management. Data pipelines is more or less we are data centric as the company. We want to like send the data to all clients within their company and so on and so forth. Now let's move to the next slide. It sounds a bit, it looks a bit complicated, but it's an overview, and you can like later on check it. But let's look at a couple of examples. So on the left side, you have a data sources. They're listed, and you see those dots. They can go on. It depends on the use case. But the first one on the top, it's OLTP, so transactional databases, and CDC, change data capture, so the data that you may get. Then you have like ERP systems, then have events from the processes, which are anyway also transactional data. Then you may have a logs to analyze. Then some third-party APIs that you would like to integrate, like weather data or whatever. Then some file storage and so on and so forth. This is like your sources. Then you have sort of multiple ways how to deal with that. So, and they are listed here. Yeah. For instance, let's stick to something like a Python libraries. So there are libraries who could deal with the data ingestion and transformation. What it means? Data ingestion means you read data from somewhere and you put it somewhere else, from moving data from A to B. Why ingestion? It just sounds cool. Then transformation means what you do with the data to fit it into your format. I explicitly mentioned Python and explicitly mentioned pandas, because if you have something really simple, so like you saw the system that you dealt with during the lectures. If you work on the exercises, when you click on the button, you get a table or tables with the data populated within your database schema. Behind it, it was a Python script that just filled the tables with the data. So it was the easiest option. But if you need something complicated, so like real stream processing, then you need to do a bit different, more complicated stuff like AVS Kinesis or Pulsar, or the most widespread option nowadays, Kafka. Or you can also use Spark for that. It's also widespread. So if you just dealing with the connectors of the cloud, you can use Fivetran and so on and so forth. So it depends on the site. It doesn't mean that you need all the tools. It doesn't mean that you need to know all the tools. It's important for me that you will at least hear them and understand, okay, Fivetran is a new unicorn in the Silicon Valley, and what does this Fivetran is actually do? Fivetran, in this particular case, is nothing else as the company that deals with ingestion and data transformation with the focus on the cloud use case, let's call it like this. So I have a company, I have a lot of data during the last 20 years. Inside my databases, I have petabytes of the data, and I'm struggling to put the data in the cloud. So I will get rid of a couple of problems that I have with my infrastructure, like scalability. And Fivetran is helping such companies. So, as I mentioned to you, the idea is the same, but the view on the problem is different. Then you have a storage and historical storage. You see a classical way, a data warehouse. So it could be what you see here, Snowflake, BigQuery, Redshift are the examples of cloud-based solutions for sure. But still, no one prohibits you from hosting your own one. Then you have some data lakes. I won't stop on that a lot because it's really, usually you see this S3, GCS, HDFS. So it's really, really huge data storage systems with a lot of data. Then you have something like between the historical data and prediction, so like some data science platforms. Finally, we get to the point. So there are a couple of them. Like during the exercises, you were asked if you wanted, you could install an Anaconda, for instance. But Anaconda, it's a good and open source tool. There is no but. I want to just explain you a story. I checked a couple of other data science platforms last year, I think it was, or yeah, that were mentioned by the Gartner. And when you look into them in details, like IBM or Domino's, so what they do, they are taking the Anaconda and Jupyter Hub and Jupyter Notebook as the core, and they are simplifying the work with the data science workflows. I will not say that it's only what they're doing, but it's what primarily they are doing. So, like simply speaking, you get a service, and in the core of it, in the heart of the service, you have an Anaconda or some similar tool like Pandas, Jupyter Hub, Jupyter Notebook, and around it, it's a custom code of a company. It's totally fine. Then ad hoc queries, real-time analysis if you need one, and output. You already saw the output, and there is really, the options are almost endless regarding the output. So the simplest one could be, as I told you, generation of the reports, still the real-time analytics with some pop-ups, and so on and so forth. It does not mean that you need to know all of them. I hope that you will grasp the idea that tools and approaches could be even complicated, depends on the case, sophisticated, depends on the use case you're speaking about. It will help you to understand why people created in-memory databases. So introduction to in-memory databases. I already teased this last lecture that I have. On the left side, you have disk spinning database. So it's basically if you need a block or if you need a row out of the table, and if table is not somewhere in the memory, so that database will have to wait for the disk to rotate, to spin till it will reach the block, read it to the memory, and then you will get the row. And if you're fetching a lot of data from different blocks on the disk, what you see, so you have a concurrency problem, and you have physical limitations of rotations of the disk, so it can't rotate endlessly. You will say, okay, we have SSDs. Yeah, they're a bit faster, but still they are sometimes not that robust. They are used, and they're still really expensive. On the right side, you have something different. You see, okay, we have no disk anymore, which is not totally true. You say all those blocks and so on and so forth, they're directly inside the random access memory. So it means if you need a table or if you need a row, no waits for the spinning of the disk. So immediately get served for the data. Still, disks are used to back up the data, so we don't have to forget that those databases have to guarantee the ACID principles: atomicity, consistency, isolation, and durability. The question that I always asked myself, why you can't simply transfer the non-in-memory databases into in-memory databases? Why not? The answer is not easy, but the genuine answer is the last 50 years were invested in the research and building on disk databases, and you can't simply throw it out of the window at once. It's not possible. Why I explicitly mention on disk systems. So all the algorithms, all the approaches, all the optimization indexes, everything that is behind the database were optimized to work with on disk system. And you can't simply switch it off. It's not possible. So if you do it, the database will simply stop working. And to create a memory database, you would like to write or implement a completely new database with the new paradigm. And it lasts a couple of decades till you get a really good version that is sustainable enough so you can sell it to your clients. if you are a huge corporation. But still, I hope I could explain why it's not possible. So this is the background I already mentioned to you. I already mentioned this as well. Problem with the buffer pool, it's spinning the disk. And for instance, there is something assets, and particularly there is something like write ahead logging. So it's a technique to make sure that nothing get lost. So it's like a protocol of the database for logging and recovery. And yeah, you can sort of trick out the in-memory database to handle this wall in the proper way, so it will not block your transactions. I already, I think, mentioned it or not. So this is basically how it works. You have on the right side, you have a disk system. So it's called slotted pages. So it's basically some chunks of bits and bytes that are later on transferred by the database into the real rows that you see into real data. Then you have something like buffered pool. And then you have something called index. And this all mess have to work on the disk because the only true data is on the disk. And the management between index, buffered pool, page table, and so on and so forth can be simply neglected. I already mentioned the guy, Andy Pavlov from the Carnegie Mellon University. He's a famous researcher and educator in database management systems, so including in memory databases. Once he did research to understand how much time does a particular database, in this case PostgreSQL, spends on real work. And real work means answering a real query. So it's simply 12% of the real work. The rest is managing the database. So really, 89, almost 90% of the time, database works to guarantee the ACID principles. Yeah, for sure. If you know this, the first idea is why. Let's get rid of all those stuff that we don't need. But the question that you have, how? And that's how particularly the in-memory databases were created. Yeah, I already mentioned it to you, so I'll just skip it. You have heard about the big data. It's a big buzz, used to be, and still there. What is important to know for you? So it's big data. It's not about the data only, huge amounts of data. It's how the data grow, and you have a different data. So different data means you have different data coming from all over the world that you could potentially analyze. And what is also important here, two aspects that are not part of the definition, but still are they as the players, technologies, special technologies, and analytical methods. Well, I already mentioned you technologies. So just remember the previous slides, I mentioned you concrete technologies that are used to tackle a particular problem, like data ingestion. I never spoke about the analytical methods, but I just want to mention you one keyword that you may hear so far. I won't use artificial intelligence, but deep learning. So deep learning is a set of algorithms and methods that are empowered by the data. And this is what driving the market nowadays. So once there was a guy, a researcher, he called Jim Gray. Once he said tape is dead, disk is tape, flash is disk, RAM locality is the king. So basically, it means if you need to get data as much as possible to the RAM to be efficient. But the problem that you have is the faster your memory gets, the more money you have to give out for that. Let me speak here about the processors. You know, the processors consist out of resistors, and the resistors could be used as the logical processing units, or they also could be used as the memory. There is also some memory in between, so-called fast memory. So you see here CPU registers and CPU cache. Sometimes the drawback by the engineers. So you have a crystal to grow with the resistors, and you have to decide which part of the you need more memory or you need more speed. If you need more speed, so it means you will use more registers for calculating and less registers for memory. But sometimes it making no sense if you use fast in calculating, but you have no data to work with. So I mean bits and bytes, so it's useless. And vice versa, it's also the same. You're full of data on your CPU registers, but you can't process it because you're lacking the registers. And this is the drawback the engineers are having, but it's not our problem. I just want to know it. So I just want to let you know it. So just give you some numbers. On the bottom, you have read 1 megabyte from the disk. So how fast? You have 20 milliseconds. Yeah, it makes out something like 20 millions of nanoseconds. And fetching L1 cache memory is 0.1 nanosecond. It's really fast. So the natural idea, the closer we get to our CPU, the faster the processing could be. But I just explained you can grow the memory of the CPU endlessly. You can put terabytes of the data into it. But there is still a hope because we have a really fast memory, like main memory, that is not that slow in comparison to CPU. It's not that slow as the disk. I'm not saying that disks are bad. It's like simply the reality is that CPUs are faster and RAM is also fast. I won't stop on the market drivers because I mentioned it to you, all the trends, all the buzz around the artificial intelligence, big data, self-service BI, and all that stuff, and to some extent about the in-memory databases. If you attended a lecture last week, the Bjorn mentioned that they have a branch sitting in Nuremberg, and they're working with a database called Exasol. Exasol is a memory database, and it's used in different use cases, and it's really fast, and really costs a lot of money. It's a small company. It's not an SAP. It's SAP HANA, and they are really changing the market nowadays. So, like for instance, by integrating more intelligence into a database. Yeah, exactly. I was too fast speaking about the Exasol. Later on, I will speak on HANA, but I think it's unfair to mention only one particular tool. You have to know that there are multiple tools exist. Exasol is nowadays penetrating the market or widespreading its influence on the market faster. So why? Because people are willing to give out the data for faster databases, and they are also used for analytics. And for instance, you can't serve the clients if you have a lot of BI clients using a web-based or online-based analytical system. You can't or self-service BI, you can't let them wait too long. And if you don't want to let them to wait too long, you need some kind of really fast data storage. And there are a couple of options nowadays, and Exasol is one of them. Another option is HANA. It's called Platform. Actually, Whether the Exasol is also, I think Exasol is also could be seen, could be treated as a platform. Why? I can explain how you could treat a database as a database or as the platform. If your database can do stuff like sending an HTTP request out of it, handle more than SQL. So like in case of SAP HANA, you could run an JavaScript engine inside the database. So you have two processes of the database process and runtime for JavaScript. So, and they're natively integrated, so you don't need anything to connect to the database out of the source code. This you could say as the sub platform or appliance. In case of Exasol, I think you could use Lua. Lua is programming language. It's a bit limited, but still really powerful. I think that they use Lua, but I'm not quite sure. I have another database example that definitely use Lua as the programming language. But this is not all that you usually get. Again, it's not a marketing, it's just to let you know what you can do with the database. Within the HANA, you can also use an analytical stuff. So they have a library called PAL, predictive analytical library. It's basically, you have a tools or implemented for you machine learning algorithms that you can use out of the box. So there is a next lecture where speaking about decision trees, and you have a database with the tables that you want to use for your predictions, and you don't need to move the data out of the database. You can run the predictions inside the database. So it's really simplifies your workflow. But you have a disadvantage. In this case, you stick to what database offers you. You can like use whatever you want, but you have a huge benefit because usually all standard things are implemented, like principal component analysis, some kind of clustering, k-means, c-means, whatever, dbScan, some optimization techniques, some linear optimization techniques, some even neural networks are also implemented in case of HANA, and they will be extended. It could be tough to use because it's not new, but it's still under development. Again, this is the sense of appliance. You get everything in a box, and you can use everything out of the box. You can create a user interface. You can process the data, and you can analyze the data, and you can serve the output of the analysis to the users, to your end users. We used to have exercise on HANA, but no more because they are changing their policies too fast. But still, you can use a free tenant thing from SAP. It's now called SAP Cloud. You can log into there and get free instances to play with. Tarantul is another one. So I mentioned you two databases that are proprietary, and Tarantul is a non-proprietary open source database. So it's also like really powerful in terms of the people say, okay, we have database, let's put everything the database have into the database and more, like initiate any requests out of the database and so on and so forth. So it's an it's not a directly open source alternative to HANA or Exasol. It's yet another in-memory database that could be potentially used. Do you have questions till now? Are you still able to hear me? Perfect. So, I hope now you're convinced that the people invented and created in-memory databases, by the way, If you will check the database index, I think most of the in-memory databases came from Korea, whatever. Why? I don't know. I think the second one is Germany. And a couple of Korean in-memory databases were like acquired by SAP. And you remember the very first slide, the SAP strategy to buy the companies and the technologies, which is totally fine. But let's move to the view of the enterprise in the problem. So why someone would need an in-memory database? Say, we have a classical distribution of the tasks, we have a transactional system, we have analytical systems, we know how to combine them together, and we're happy. So why you should use a database, in-memory database? I already mentioned you a couple of reasons previously. So speaking about the enterprise service bus, where you want to like talk onto your data source and new system, and it have to be fast, and you want it to be fast, and you want to handle it as fast as possible. But still, there is also a thing that we didn't spoke about. We spoke about it, but not about the problems of the ETL. So you have an OLAP system and OLTP systems, and there is an ETL running between them. OLTP and OLAP system are changing with the time. So it means the ETL also should change, that or data pipeline, whatever you call it. And changing what combines those systems could be really a tough and cost-intensive task. Cost-intensive not only in terms of licenses, hardware, and time, it's also cost-intensive in terms of manpower that's used. And this is one of the reasons why one would like to combine OLTP and OLAP together. And you know that it's hard to do. Why? Because there are some systems, usually database systems, that are more dedicated to cope with a lot of writes, and there are writes, I mean transactions, and there is other type of systems that are more dedicated to deal with the lot of reads, so analytical systems, and it could be hard to combine them. And the idea is, let's put everything in memory and forget about the problems of the ETL. There's also an additional benefits of such constellation. For instance, your queries became really fast. So I read about, it's again part of the marketing, maybe I didn't measure it on my own, but people are claiming that their performance of the boost on the heavy SQL queries were like not 10 times, not 100 times, 1,000 times faster. I'm not believing in this 1,000 times faster, but I will buy it if they say to me, okay, it's like 500, 200 to 500 times faster. It's totally feasible, but you can always create a benchmark that you will prove that this 1,000 times faster. But anyway, queries are faster. It means even without an indexes, they're fast. If they're fast, it means you don't need to use any other tricks as you used before, like aggregated views, not aggregated views, sorry, materialized views, so where you pre-aggregated data to solve them fast, so you just get rid of some layers, which simplifies the design. And there is why it was possible. So basically two reasons, or yeah, two reasons. The cheaper hardware, like RAM, CPU, and multi-core CPUs. Why two reasons are important? Because if you had just imagine that you had no multi-core CPUs, just a single-threaded ones, or not that widespread, and you still have data in memory. It will not help you that much. Why? Because you can store the data really fast. You can bring the data to CPU really fast, but your CPU is slow because it can handle the stuff in the parallel. That's why two aspects are really important. Then I have a slide on the core concepts of in-memory databases. I will speak about the core concepts and go through them, but I won't stick to some examples. So why I need those slides? Because I want to convince you, if you have a possibility to use in-memory database, try to use it. So first of all, it's combined. Again, it's not only about the in-memory databases. It's also about general non-in-memory databases. So some aspects are also true for them. Combined row and column store. What does it mean? So this lecture, during this lecture, we're speaking about physical representation of the data. And I already mentioned you the spins of the hard drive when you read the data out of it. And while we're speaking about the spins of the hard drive, it's important how the data is located. You can locate the data in row-based form or in column-based form. What does it mean? Row-based form means you have some index on the disk, and all the values that belong to a particular row will be saved to that place. In column-based, in column, sorry, I'll just move to the next slide so you will understand. Just imagine the table on top. You have a country, customer, product, and piece, and you want to save it somehow physically. Row table means you have a row 1 and all the values here, row 2 and all the values here, row 3 and all the values here, and so on and so forth. In column-based table, you are looking at columns, not in rows. So all the columns are combined together. All the columns are combined together, all the values of the column. What is the benefit of such approach? The huge advantage. Usually, when you are reading the data, you don't need all the columns. Select star something. It's really not a good query. For exploring the data, fine, but not for the real productive system. Usually you specify the columns, and usually you want to do something with those columns. And that's why combining the data within the columns, not within the rows, could be a really huge benefit for the analysis. But writing the data to such columns could be really a tough task. Let's move to the next slide. This is how it's organized on the disk. On the left side, you have row tables. So you put a row and you connect the row to the next row and so on and so forth. And in column tables, you put a column and then all the values that are related to this column put together. So, and I think one seq, one read from the disk, a single call. It depends on the system, but it's usually 4 kilobyte. So, and in one seq, in one read from the disk, you could read 4 kilobytes. And if inside the kilobytes you have all the values that you need, so because it's a column that you asked for, then you don't need to perform any more disk operations. And in case of row, it will be hardly possible. Why? Because you need to read all the rows that are connected to the value that you're looking for, and then throw away what you don't need, and then keep the column that you asked for. So quite inefficient. I hope it's more or less clear. And this is not applicable only to in-memory databases, it's also applicable for the on-disk systems. So, and it's believed that in a couple of decades, the column-based systems are going to replace row-based systems, but it's like not important for now. Any attribute as the index, it could be a bit hard to understand, but you don't need an index. speaking about the in-memory database, you can use any attribute as the index. How it's possible? Uh, Inside the memory, you have always a start point, yeah? And you always have a type of the data that is stored inside a column. And basically, to find a particular value within this column, you need to run a simple calculation. You need to calculate an offset. So, example, assume that you start at 0 and you have indexes, integers. An integer is 4, it depends on the system, but let's say the small integer is 4 bytes and you need the fourth integer. So it means if you start at 0, the fourth integer will start from the byte number 17. Yeah, 4 times 4, it's what you have to. No. If you need a fourth, then it have to be 3 times 4, and then the 13 byte is going to be the first byte of your integer, and the rest 4 is the bytes of the rest of the number. So, and by calculating these offsets and this reference is really fast. It's that's why you don't need an index to reference to a particular value, and you don't need to have an B tree or similar to search through, because full scans are totally fine because it's really fast, it's in memory, and you always, if you need a particular value, you always can calculate the location of the value. Then insert only. It's also not only true for the in-memory databases, but for the rest of the databases. So insert only basically means you don't delete the data, you just put on new data and mark the old data as outdated. Why it's needed? The most expensive operation for the database is update or delete. Just to why? Because again, because of our ACID principles, atomicity, consistency, isolation, and durability. So, what means consistency? Or let's stick to the isolation. Assume that you have two transactions and they want to have the same value. And this value, one transaction is going to update the value and the other is going to read the value and do something with that. Which transaction should come first? First one or the second one? There is a special algorithms and methods to handle it, but whatever algorithm you're going to use, one transaction is going to block another transaction for some certain period of time. To avoid this, you can get rid of the update and say insert, and that's why those blocking mechanisms could be handled faster and easier, just to let you understand how its potential could be used. Then we have multi-core and parallelism. I already spoke about it, I will skip it. Then lightweight compression. So the motivation behind the compression is that despite everything is nice and cheap, we have everything in memory, but we're still not able to put everything that we have inside the memory. So like instance, we have an SAP HANA appliance that may have 400 gigabyte of memory or main memory, and will have, I think, 60 terabytes of disk space. And you would like to put as much data as possible into memory to run it, to be able to run your analysis faster, even if data grows. And lightweight compression is something that lets you to do it. One of the simplest one is dictionary coding. You can later on check the slides and see the numbers, how you could potentially optimize the table. So you don't need to do it explicitly. The database will handle it. But it's good to know that such mechanisms are existing. So it's like now we have benefits of not only getting rid of some pre-aggregates and some data that we don't need metadata like indexes. Now we're even able to compress the data and the compression costs us nothing. Why? Because we sometimes even able to work on compressed data. So if you will compress those names, by the way, handle strings is also a tough task for the database. I'm sorry. Handle strings is a tough task for the database. That's why even transferring those strings into integers and handling those integers and only put strings back out of your dictionary to those integers can be could boost the performance. So the question that, so it's again thought experiment. Just imagine that you want to save the data about all human beings on the earth, and you are going to use 200 bytes per single for each single person. We just want to see how good the compression could be, even this dictionary encoding example. So dictionary encoding example means you know all the dictionaries, and if you see the word, you can assign an integer to this word, and later on you can use this integer instead of the word later on. So this is basically the idea. Then if this is the plain side, just let's look at the total. So just you can check the numbers later on. So if you 8 billions times 200 bytes, you'll have 1.6 terabytes of the data to save, just basically the information about every human being on the earth. So it's against GDPR. It's indifferent. It's just a thought experiment. And now you apply the dictionary encoding, and you get almost I will say 70 times less space occupied just by applying the dictionary. You can figure it out. You may ask me how you came up with this dictionary and column. So it depends on for sure, the names and so on and so forth. And you can even, it depends on the use case that you deal with. But in case of, for instance, gender, you have simply one bit to encode, and the dictionary is quite simple. Not nowadays, it won't be nowadays binary, but it's a bit old example. But still, it changed nothing to the database if you add other types of genders here. But still, it's a thought experiment. As I already mentioned to you, there is no aggregates, so you don't need them because you're really fast. And no aggregates means less space, which is cost a lot. Reduction of the layer. So this is quite important to understand. I think each new layer that you add to your system makes your system, whatever system you're speaking about, a bit more complicated. And by using the in-memory databases, you're getting rid of some layers. For instance, you're getting rid of the layer that deals with the ETL, for instance, or you get rid of the layer that deals with just a second. You get rid of the deals with aggregates. Yeah. To give you again the sense how much you could potentially save on the time. So you see this architecture. This is also another view how a modern architecture could look like. On the top, you have some users that are just doing the transactions, yeah, and you have some numbers here, yeah. So each transaction is going to be saved. So you see the transaction after 300 milliseconds inside your database. Yeah. The database is a transactional database. Then we know what we need to do. We need to perform an ETL or change data capture mechanisms. Now you immediately have a gap of 24 hours. So because it's usually depends on whether you run your ETL every hour or each day. So now you have changed data capture and ETL, and it means 300 milliseconds plus 1 day. It's when you have the data for your analysis. Then you have the data for your analysis ready, but you don't have an analysis yet. So like no reports or something were generated based on the data. Then depends on the tool that you're using, BI or whatever. So you have another, you will spend another amount of time to generate such reports and then show it to the user or whatever. This is like when we have a single location. Now imagine that you have 2 or 3 like different locations where you have to use to integrate the data. First of all, it's a really tough task even to capture those changes. So using the database, you can use vault replication or something. So write-ahead lock. So it's a lock of the database so that you can use to synchronize the databases. So it will make a bit slow your database, but it's not a big deal. It's still not days or whatever. So it's still here speaking about a couple of minutes. And then we also have data here in another system, another ETL process, and another data warehouse or whatever. And basically, reports in another system will appear a bit later as in initial system. What is the purpose of this example? The purpose of this example is to show you when you get rid of this, for instance, this layer, the ETL layer or whatever, and you'll directly run what you want on the database, you can get rid of all those time gaps that you usually have. It means, basically, you remember one of the, it's not at the first slides, but when we start, the faster you can react when you have the data, the better your reactions on the better your actions should be. So we're not speaking about some random reaction, we're speaking about the data-driven decisions, which is quite crucial. So this is an example to show you how getting rid of the layers could improve the overall process. Then another one that we have as the benefit, it's no disk. So obviously I won't stop on that because in memory database we have no disks. Actually we have disk, but it's used for the backup, or as they say, the researcher and the developers, for persistent storage of the data. Why? It's nice and good, but if you turn off the electricity, the data is gone. So you can recover the data because it's in memory. And to address this problem, you have a disk anyway. You can improve the performance with SSD or any other flash technology that could persist the data. But still you need a disk. But again, the difference is that it's not your primary storage. It's a secondary storage that is used sort of for backups or to secure the transactions while when the power outage happens, as we have 2 weeks ago in Oldenburg. I don't know whether you know about it or not. So there's also some other generic stuff left, but they are not fully relevant for memory databases. I just wanted to mention it to you, a couple of them. So for instance, this one on the fly extensibility. So when we are using SQL, we're speaking about the data manipulation language, DML. There is also a part of the SQL that deals with the DDL, that changes the structure of the table. And assume that you have a couple of tables. You have a fact table, and there are a lot of transactions running using the fact table, obviously, and you need to change the fact table. Like you need to add an additional row to the table because you have a new dimension or whatever. So this kind of operation is going to change the structure of the table. And the point is that when you're changing the structure of the table, no other transaction is allowed to use the table because you're changing the structure. So all the rest of the transactions usually should be blocked. It used to be like this 10 years ago. Nowadays, I think it's a bit more flexible. But still, if your fact table is huge and if you populate it with the new column, it could take, depends on the table, from minutes to hours of the time. That's why extension on the fly for a memory database is a huge benefit. So you just simply, by nature, by design, you don't have the problems that you usually have in a normal database. So the last slides I would like to spend speaking about projects that we did that are related to it. Maybe it's interesting for you, maybe not. 2 weeks ago, Michael spoke about layered scalable architecture of the SAP. Yeah. So this is how it looks like on the left side. So you have basically different layers. So you have visualization layer, reporting layer, business transformation layer, data propagation layer, quality and harmonization layer, data acquisition layer. Then you have corporate memory and operational data store, ODS. Fancy names, but if you go back to the slides with the modern architecture, you can find all the layers there as well. And this is exactly the mapping to the info cubes that are used inside the SAP. So this is like if you split your application or your data warehouse in those layers, you'll get enormously you will get a lot of benefits out of it. And this is used to be a master thesis where we did the following. The student look at the following. You have behind each of layer, they could be or could not be a database. And we looked into the following problem. Sorry. How a particular layer could be changed or is going to be changed if we introduce SAP HANA into or in memory database in such constellation. And this is what we found out. So it's like analytical and practical approach. So in some cases, you don't have any kind of benefits, but there are high benefits on some layers, like reporting. So on the reporting, you have a high benefits on the query performance, and you have a high reduction on tuning mechanisms. And you also use less virtualization, so you are forced to use less visualization. So it basically means I just wanted to make a following point. I just spent last hour speaking about how nice and good in-memory databases could be, but it depends on your use case to decide whether you are going to use it or not, whether you are going to benefit from it or not. And in this particular use case, you see, you have an ongoing running data warehouse, and the question is, should you migrate or you should not migrate? And you see the table and understand, okay, I'm really struggling with business transformation, reporting, and visualization. And if I will migrate, I will get an enormous boost in these domains. So it was it, so we'll migrate. So this is how one could interpret such results, or how you should make a decision whether to use a particular technology or not. Another example that we did, sorry, it's to run an analytics inside the HANA, and basically we create the following. Actually, not me, I was not involved back then, but the students did it. So again, you have in the core, you have a data storage and data mining here. And back then, it's still existing. Back then, the HANA could connect itself to Air server and to run analytics inside the Air server, which is really amazing. Why? Because you don't need to transform the data. You need to do nothing. You need to just run an SQL and call an R script, and you will get the data inside the same windows or the window of the database. The put on top reporting self-developed. So there is something called SAP UI, which is not existing, I think, or it's existing as sort of open UI 5. It exists, but it's mostly replaced by for commercial projects. It's replaced by Fiori. And we have also Excel here, which is still a useful tool for reporting, not for data management. And the bottom, you have a custom ETL tool, which used to be back then, and after that, a problem for the HANA. But now I think they sort of, when we're speaking about the cloud solutions, they sort of solved the problem. And they used also Pendaho here, which is known nowadays as SPI. Pentaho Data Integration Server. I'm done for today, and we look into some physical modeling techniques, and we looked into in-memory database systems. I hope you learned something new. I don't know whether you're going to use those databases or not. They used to be hype, and now they're like sort of like a 15 years ago, cloud used to be hype, and now then it was dehyped, and now it's like again hyped a lot, but due to smart services and services running inside the cloud, such as Lambda and similar. Uh, I'm not speaking that the hype on in-memory databases is getting back. I'm saying only that it's not hype anymore. It's more or less an reality, and you have to be aware of this reality. And yeah, I'm done for today, and see you next week. And last announcement: I'll try to check all your submissions till Tuesday, so you'll have a feedback from me till Tuesday. I mean the exercises. Do you have questions? And we will go on with another lecture next week. So I don't think that we will need more than half an hour or 30 minutes. I uploaded the slides for the next week already. Do you have questions? If you don't have questions, then I have to leave the lecture now because I have another appointment at 10. So I have to be there. See you on Tuesday and have a nice day.